Okay, so thank you for your coming for this second talk of the mini course Stochastic Geometry and Statistical Mechanics. So yesterday we saw the area process, which is a good example and a quite old example of models between stochastic geometry and statistical mechanics. And we talk many times about Gibbs measure, like a limit of finite volume Gibbs measure. And so maybe it's not so a good definition for an object. An object is defined by a limit, it's not so nice. And it's possible to define directly what is a Gibbs measure on the infinite volume. For example, if I give you a measure on the infinite volume, an infinite point configuration, what is it, a Gibbs measure or not for the energy we consider. So, and for that there is an equilibrium, well-known and quite old equilibrium equation to define what is a Gibbs measure. It's the DLR equation for Dereudre, Lamford, Ruel. So I would like to present this setting today and to present a way to prove the existence of this Gibbs measure. We will see also an equivalence with the limit of the finite volume Gibbs measure. And I will present also a new modern way for proving the existence of Gibbs measure. The existence of Gibbs measure is quite old problem, and it was solved by Dereudre, Lamford, Ruel with superstability arguments and so on. And recently, with my collaborator Dereudre and Hans Otto Georgi, we give a simple proof of the existence of Gibbs measure and a more general one, which is well adapted for stochastic geometry problem, stochastic and statistical mechanics problem. So today I will present a simple the way to prove this theorem, but in a simpler setting than in the paper with these guys. We'll see simple assumption, but it's contained, for example, the process yesterday, the area process for beta positive and negative, and many other models. So we'll see that. Okay, so so the space of configuration is always noted omega for point configuration and locally finite point configuration. And now the first things we have to do is to define the energy. The energy we are interested in. And so it's called, we call that H, or it's Hamiltonian for capital H. It will be in this talk only just a function from omega f to R union plus infinity. And for omega f is just really finite configuration. The space of finite configurations.
The configuration of points on
of points, yes.
Euclidean space.
Yes. Finite configuration of points, yes. So you are in general in RD, or you can be in more general space, but so for a configuration, a finite configuration, so you can define the energy of this finite configuration, and it may be equal to plus infinity. Okay. Let me just start to introduce the first assumption for this talk, is stationarity. our construction will give a stationary Gibbs point process on the space. And the tool we use is the specific entropy, which is defined only for stationary probability measure. So the general setting of this construction on this stuff here is the stationarity. So stationarity means this function is stationary. It means if you consider a translation, so for any finite configuration and any x in Rd, so the energy of this configuration x is equal to the energy of the configuration omega plus x. So it means just a translation.
What is the meaning of this subscript f? So you want to highlight it?
It's for finite.
Okay.
Omega f, it's for finite configuration. Here, it defines energy for finite configuration for the moment. Okay? And it's just to translate the configuration with x. Okay? It's clear? Yes. So this is the first assumption, stationarity. But yesterday the model was stationary in space. Okay. Now we need other thing because we have in mind the finite volume Gibbs measure. It's not the object we try to build, but we have it in mind, of course, is of course for lambda p lambda 1 over z lambda exponential minus capital H lambda p lambda, where p lambda is Poisson point process on lambda with intensity z. It's an homogeneous one, of course, by stationarity. Okay, so we have in mind this measure here. So we see first natural assumption here is clearly we need z lambda, which is defined by the expectation, the integral of exponential minus energy under the Poisson point process. We need that this quantity is finite because okay, and also it's not so obvious, but in general it is the case, non-null. If the energy, for example, is equal every time to plus infinity, always equal to infinity, this quantity is equal to 0, and it's not defined like a probability measure. Okay? Okay, so for that, to ensure that, classical assumption in statistical mechanics is the stability. So our second assumption, maybe I can put a color about the assumption. Stationarity, and now stability. So for this part here, it's classical to write for any finite configuration, the energy of this configuration is bigger than minus a constant times the number of points. So there exists a constant C, positive, such that for any configuration, the energy is bigger than minus time number of points. Okay, this quantity is the number of points. So maybe just it's quite okay. It's the first assumption. You will see in a second why it ensures that. And the second one, to obtain this part here, the simple thing to do is just to assume the energy of the empty configuration is equal to 0. So empty configuration, no points, so we put the energy is equal to 0. So it's quite simple to prove that exponential minus h lambda p lambda is equal to the sum exponential minus z lambda. Sum for k is equal to 0 to plus infinity, the number of points in lambda. Multi-type integral on lambda to the power k, and exponential minus the energy, and the energy is bigger than that, so here we can dominate it by c times k, and z to the power k dx1 dxk. So this one is smaller than that, and sum over k, and this quantity is smaller than exponential c, the Lebesgue measure of lambda to the power k, and something z is missing. Okay, so, and this series is convergent, so this one is finite.
Wait, but isn't the number of points just a Poisson variable?
Yes, the number of points is a Poisson variable, so it's just z to the power k, something is missing, k factorial. Okay.
Why it's lambda to the power k?
The lambda to the power k is because you integrate here. This we integrate here. The number of points is a Poisson with parameter z times the volume of the lambda.
Right, but basically what you do, you just compute the Laplace transform of
No, it's
Poisson.
yes, but here it's just to write. You have just to compute this quantity. You don't need Laplace transform here to solve this simple thing. So this one is finite, and after that, so z lambda is equal to that, and z lambda is bigger or equal to 1, the probability measure of the empty set for the Poisson, and this quantity is just equal exponential minus z lambda. So it's clearly strictly positive for the other cells, for this part. Because for the empty configurations, the energy is equal to 0 here, so there is 1, and the volume for the Poisson point process of the empty configuration. Okay, so this condition stability here ensures that this partition function is finite and non-equal to 0. Okay. Okay, so it's a basic assumption. For that, maybe about this stability. Okay, no, I follow with the assumption. I will give example after. Okay, it's okay. So for simplicity in this talk, so this one is quite standard and for more or less all models. I will impose here a finite range assumption. It's just for simplicity to be able to do all the calculus quite simply. And the finite range assumption claims the range of the interaction is finite. What does it mean? It means there exists a range R, such that for any lambda in Rd, any lambda prime containing lambda plus the Minkowski sum of the ball here. So it means you consider lambda somewhere and a lambda prime here which contain lambda plus the range here. Okay? So we can, and for any finite configuration, so the energy in lambda prime, so the energy of the configuration in lambda prime minus the energy in lambda prime without lambda. So it means the energy here minus this one. So it's more or less the energy of this point here with respect to the other one. It's what is the energy we have to, what is the energy when you, this quantity here is the energy of the full configuration here. Okay, this quantity is the energy of this configuration here without the point here. So this quantity is the needed energy to put the point here. Okay, we can see this quantity like that. So the claim is that, so it means it's the energy of the point here with respect to the outside configuration. And the assumption is this configuration, is this energy is equal to the energy of this quantity here minus, so the same one here minus lambda. So let me just explain here. So I explain this quantity represents the energy of the point here, the energy to put this point in this set lambda here with respect to the other points. It's a difference of the energy. And we claim that this energy of this point finally does not depend on what happened after the boundary here. Okay, because this point here has no influence in this difference of energy. And it is what we call finite range interaction. Okay? And this quantity is simply called h lambda omega. So this is a definition. And we can say h lambda, capital H lambda omega is the energy of points omega lambda with respect to the point omega lambda complementary. Okay, it's a finite range. So now keep in mind capital H without lambda here, it's the full energy of the configuration. Okay? And capital H with lambda, it's different, is the energy of the point inside lambda with respect to the outside. It's a difference of energy with this point, without this point. Okay? It is clear? Can I go on? Okay, so it is the second assumption, the finite range assumption. Okay, and okay, maybe something is missing here to give this definition.
Shouldn't you raise the prime in the last expression?
Okay, sorry. Thank you. There is lambda plus B0 R, yes, of course. It's better like that? It's the energy here minus this one, and it's equal to the energy here minus this one. But is it sure that this difference of energy is defined? It's not clear, because maybe this one is equal to plus infinity, and this one if this one is equal, for example, to plus infinity, and this one is finite, the energy is equal to minus infinity, which is sense length in statistical mechanics. So here we have to assume a kind of hereditary. It's the same assumption as hereditary yesterday. If the energy is finite, it's always defined, but here it's we need a hereditary. It means if the energy of omega is finite, maybe is equal to infinity. If the energy is equal to plus infinity, it's unsure that the energy of omega union x is equal to plus infinity. And that for any omega and any x. So it's quite standard also. If the energy is equal to plus infinity, if you add a new point, it's still equal to plus infinity. So this hereditary gives a sense for this difference here in any case. Okay, so
another confusion. So in the very first definition, you allow your energy to be negative.
yes, of course. The energy can be negative, but not minus infinity. So energy is classical. I will see example for which the energy for the Lennard-Jones potential, for example, the energy could be negative. Yes, of course. Okay, so on the blackboard now you have the 4 assumptions for the talk today, and for this with these 4 assumptions we can prove generally the existence of Gibbs measure, and I will give you the proof with a lot of details to be self-contained proof here today. So let me just recall, stationarity is just an invariance translation of your energy. Stability classically means the energy is bigger than minus time a constant times the number of points. So you can see it for the energy can be negative here, but you have a lower bound which is minus a constant times the number of points. Okay. Finite range, it means the energy of in lambda with respect to the outside, which is defined by this difference, is depends only on the boundary here, with a distance r which is fixed, uniform for the configuration. And hereditary, so it's quite standard assumption. So all the assumptions are very usual here. The only one which is not really satisfied for all the models is the finite range. Sometimes infinite range interaction appears, and so it doesn't cover today in the talk. Okay.
Could you give some examples of each?
Okay. Now the examples.
I see two, the number of points and the area, yeah?
For example, the area, yes. But
there are some
It's good to have examples. So for example, the area yesterday is included. Area process with beta positive or negative or positive. So both are included here. It's clear. Stationary, it translates the volume is shift invariant. Stability, it's because the volume of each ball is bounded. So the energy is bigger than minus, it depends if beta is negative, minus beta, the volume of each ball, times the number of balls. So it's clear. And the finite range, maybe if you consider only the difference of the volume when you have the balls. We put balls here. We consider the difference in volume of the balls here without this configuration here. You can see clearly that the balls here do not affect the difference of the energy. Only what happened here on the boundary has an influence. Okay? And hereditary, it's clear because the energy is finite. A more general example here, for which I work a lot, it's the Kerr-Mass model. The Kerr-Mass model is just a generalization of the area process, and it's defined like that. Consider the energy of a configuration, finite configuration, fix small r for the radius of balls. So of course the r is not the same as the range. You have to double the range, yeah, but never mind. And you can consider θ1 for the area of L omega. So if I consider just this part, it's exactly the area process. And you can add, so in dimension 2, here's a generalization. You can add the perimeter. And θ2 can be positive or negative. So now we change we try to change the shape of the perimeter of the model, of the Boolean model. This part here is to favor the area of the Boolean model, and this one to favor the perimeter of the models. And we can add also the Euler characteristic. Euler characteristic of the model. And I recall that this quantity is the number of connected components minus the number of holes. Minus the number of holes. Why this form here of this interaction is interesting? It's because it comes from the Hadwiger theorem. Hadwiger theorem claims that in dimension 2, any additive functional on the space of union of convex, because L of omega is a union of convex, any additive functional on this space admits this linear decomposition here. So it's a quite natural energy, additive energy on the space of union of convex, finite union of convex. Okay, maybe, and it's not the same parameter here. θ1, θ2, θ3 are in R and could be positive or negative. Or maybe something is strange here for the stability. Is it clear for you? This functional, okay, this one is clearly stable because the perimeter is bounded, and so the global perimeter is bounded by the number of points times the perimeter of each ball. But for the Euler characteristic, it's not so clear. The connected component, it's clear. The number of connected components is clearly smaller than the number of points. Okay, but the number of holes, it's not so obvious, but it's true. We can prove that the number of holes is bigger, is smaller than, I think it's 2 times the number of points minus 5. Maybe it will be better to check, but it's more or less, in any case, it's smaller than a constant times the number of points plus another constant. Or a constant, it's clear. In any case. But I think it's that. So you are able to control. It's not so clear. If you put n balls in the plane, is it possible to control the number of holes? And it's under linear with respect to the number of balls. Yeah. So it gives the stability of the fifth function. It's not true in dimension 3. In dimension 3, it's not true. It's not linear. So for this model here, is stable only in dimension 2. So it could be an exercise to find configuration of balls in the space, in volume, such that it's not linear. Okay, so it's one example here. And the energy is a finite range. Okay, it's just to write this difference and to check. Okay, it does not depend of the ball far away. It's clear. And it's for that and that, it's clear here. It's by additivity. For example, if you remove this part, it's false. It's not finite range. The number of connected components is not finite range, because imagine you have a very long cluster like that, and we add a new ball here. To know if you change the energy here, what you have to know? When you add this ball, the number of connected components is changing, yes or not? It depends if it's connected here. It's not connected here, so there is 2 connected components, you add a ball, so it's 1, so the energy go down. But if it was connected, so then the energy is not changing. And so the energy of this ball in this configuration depends on what happened here far away. So it's not finite range. So this one is not finite range. This one is not finite range, but the difference is finite range. It's because it's additive. So I don't check precisely that, but you can do it like you can check by an exercise. Okay, it is the first example which is covered by the assumption here.
And if you consider large dimension, we could say that instead of perimeter, we could take area of surface.
Yes, yes. Okay. And you can, in dimension larger, you can put here all the Minkowski functional. But yes. The problem is the stability.
You lose this linearity if you need this.
Yes. In dimension D, yes, it's lost there. Okay.
This is the only example, some linear combinations of Minkowski functionals.
Sorry?
Some H could be only some combination of Minkowski.
Yes. It's only one example. A lot of examples. I give another one. It's an example. No, these assumptions are quite standard. You can imagine what you want, like energy, but I give now another one. It's okay for this example? Maybe it's better for me to clean this part and we keep the assumption here. So it's okay? I can clean it? Okay. Okay, second one is more classical. It's a pairwise interaction. Pairwise interaction model. It's the classical model in continuum statistical mechanics. We consider a pairwise potential is just a function phi from R plus to R. And well, there is some assumption, but it's just the energy at the distance R. So, and it could be equal to plus infinity. So, for example, it's equal to plus infinity, and you have something like that. And in the topic here, I suppose here phi has a compact support. So finally is equal to 0 after a range R. So it will be the energy of 2 points. And now what we consider edge of omega for a finite configuration. It is the sum for all coupled in omega. Consider all coupled in omega such that and phi of the distance. So it's interaction potential energy, classical one in physics, for Lennard-Jones potential and so on. Of course, you can see, so it's clearly finite range because I assume the compact support here. And so finite range is clear. Stationarity is clear also. If you translate x, y, the difference doesn't change here. Finite range, it's okay. Stationarity. Hereditary, it's clear because if a configuration has an infinite energy, it means that probably 2 points here are such that the energy is equal to plus infinity. And if you add new points, this energy doesn't change and is equal to plus infinity. So it remains plus infinity. There is a problem with the stability. If I give that, it's not stable in general. And we need assumption on phi. And so it's quite complicated to give general things. But the assumption in general on phi is just that this one, exactly. Exists a C positive such that it is the stability condition of the statistical mechanics. So you can see, for example, the book of Ruel and or the Brochin, Lanford. So it's classical. So one easily example for which it's stable, it's when phi is positive. If the energy of 2 points is positive, of course this sum is positive and you can get here any constant, it's okay. But it's not the only one situation for which it's true. But it's quite complicated to give a precise example, but you can find in literature some example, for example, like that. For example, if an hardcore part here exists, it's automatically stable here. And in other case, it's possible to find potential like that with an explosion and a negative part like that, which is stable. It depends on the shape of the graph. So it's quite difficult to give you an example, but just for simplicity, if you want, you can keep in mind this simple example here of phi is positive. Okay, so this is a second example which is covered by the assumptions today. It's okay? Any question? Well, so we have in mind example in statistical mechanics, in stochastic geometry with square mass interaction. We have the assumption. Now I would like to prove the existence of Gibbs measure. And first, what is a Gibbs measure? Okay. So I would like to define you Gibbs measure by another way than a limit point, because it's not so natural to define an object in saying it is the limit point of this thing and so on. So I would like to give you an intrinsic definition of a Gibbs measure. So for that, I have to show you the Markov property of the Gibbs measure, of a finite volume Gibbs measure. So just recall here on the table. So P lambda, the finite volume, is just what we call here is Gibbs measure. Proposition, this quantity is Markovian. This probability measure is Markovian in the following sense. If I consider the P lambda, so maybe let delta included in lambda. So I have lambda somewhere, and I put inside delta. I would like to give you the exact form of the condition law in delta given the points here. So we have that. We call that Markovian property. Markov property. Because P lambda given, or I can, given the outside configuration, so it's a conditional probability. What is the law here of, what is the law inside delta given the outside, the conditional probability? And it is exactly this quantity here. So this thing, for two things. The Markovian property claims this quantity depends only what happened on the boundary here. It will come from the Markov property, the boundary. It will come from the finite range property. It's exactly the same thing that given it's what we call Markov property. Spatial, it's a spatial Markov property in the sense where a Markov property claims for a Markov chain the present and the future given the past, or the future given the present and the past is exactly the future given the present. Okay? So you forgot the past. Here it's the same, the spatial Markov property. The law inside here given the boundary, the present, and the past, the spatial past, it's exactly the same that the law of in delta given the boundary. Okay? So it's what we call a spatial Markov property. And we have the explicit law of this density here is just 1 over this quantity, I will explain in a second what is it. Okay. And so, what is finally, okay, the law inside delta given the outside is exactly the law in delta given the boundary, and the density and the law is given by this probability measure here. It's a Poisson law here with in delta with the density not exponential minus the energy, but the energy inside delta given the outside, which we defined before, like a difference. I think it's still writing here. It's this difference of energy. And of course, here is just a normalization constant to have here a probability measure. Okay? So this is the spatial Markov property of the Gibbs measure, which is true for any finite volume. Okay? So maybe I can give you a proof of that, but it's not too much complicated. It's just a conditional calculus. Okay? So it's quite simple, but it's a bit technical and not really pleasant to write about. You have just to consider the density here, and you consider the probability, the density, the conditional density. You have to integrate over the marginal and so on, and finally we obtain this density here, which is clearly depends only what happened on the boundary, because this function here is depend only on delta plus b0 r of omega. Okay. So it's a Markov property here. So it's true for any lambda. And for any delta in lambda. So from that, we are able now to define what is a Gibbs measure, because look at just here, this part here do not depend on lambda. So we can imagine an infinite lambda now. Okay? And it is exactly the definition of a Gibbs measure. So definition. The probability measure P on omega. So it's important now to have in mind it's omega. You can add here, not omega f. It's important now. We are now on the space of infinite configuration. Okay? So for any probability measure P on omega is a Gibbs measure for the energy edge if I just write now this definition again. If for any delta or let me call lambda. It's more natural, but this lambda corresponds to this delta here. It's okay? I can? It's because it's so natural to write lambda for the DLR equation. So, for any lambda, alors, what is important is finite for any bounded lambda included in RD. So, okay, I write like that, it's okay. P d omega lambda, the law of P, the condition law of P in lambda given the outside is nothing else than this quantity here. Okay. So now you see just a definition of what is a Gibbs measure with equation and not limit points and so on. So it's an equation. So it's an infinite system of equation because this equation has to be true for any lambda. So, and this equation is called DL1. So it's an equation because P, it's for any outside configuration. So you can rewrite it. Maybe it's not so clear it's an equation here. I rewrite you by integration, DLR equation, equivalent formalism. It's for any function f, the integral of f d omega p d omega, here for any bounded, for example, bounded and measurable function. So you test the law of P by the integration over f. Is just equal to at this double integral here. You write f omega prime lambda union omega lambda complementary. This density here and here it's the same omega prime lambda union omega lambda complementary here, integrated with respect to omega prime in lambda, and integrate with respect to the omega outside, but you can just write like that. So it's just a disintegrated formalism of if you integrate that with respect to P d omega, you obtain that, and if you disintegrate the expectation, you obtain that. So it's equivalent. These two things are equivalent. And so it's for any lambda. And so now we can clearly see it's an equation because P is here and P is here. Okay. Question? Maybe? Not now, later? Okay. So I think for the feeling of what is a Gibbs measure, this one is better. You understand what is exactly the condition law given outside. But this one is more useful when you have to do computation because it's just integral and not conditional calculus. So this one is just an integral, you have to compute that, it's better to do that. Maybe I can write on the same line here. Yes?
So by P of, so the meaning is that, so P of d omega, you actually mean the part which is, so the second
outside
is over the complement of lambda.
Yes. So you can put here lambda complementary if you want. But it's the same because you integrate with omega, but you keep only the omega lambda complementary part here. So it's the same. It's okay? And there is an equation. Okay, so it's the definition of Gibbs measure. So now what are exactly the relation with what we construct, for example, yesterday? You remember yesterday we construct a real process by the limit of finite volume Gibbs measure, finite volume model. And we obtain with different boundary conditions, sometimes different limit points. All these different limit points are Gibbs measure in this sense. You can prove it. So this equation contains the phase transition problem. It means the non-uniqueness problem. This equation contains the problem of the existence, of course, and the problem of uniqueness. So remark, there are two problems to solve: existence, it's not clear, and uniqueness.
P given H.
Yes, given H, exactly. Given H, this H is unique. It's defined, for example, for the area, like yesterday. Area, it's clearly defined. You can define uniquely that. This thing is uniquely defined. It's quite strange, but it's a kernel. It's unique, finally. But you can find different P which solves these equations. So it is it's what I say. It's the reason what I say. This equation contains the phase transition problem and the uniqueness. Okay. So finally, it's quite equivalent to what we interpret yesterday. If you have a Gibbs measure, this Gibbs measure is necessary the limit of the finite volume Gibbs measure for outside configuration given by P, almost surely by P. And reciprocally, if you have a limit point, this limit point is necessary Gibbs measure with this definition. So it's equivalent. But this definition is more practical and universal elegant because this is an equation. Okay? Okay. I'm a bit late.
But okay, so this may be a stupid question, but what you did the last time, so does it feel this idea? Because it looks like what you did in the last lecture, you considered actually different H's, or you did it. I mean, your idea was the phase transition came from changing the boundary conditions, and by doing this, so do you keep the same H or you adjust H?
No, finally it's the same H, but with different boundary point configuration. Because
you have listing different.
Yes. The edge is the same for the area, but to change the boundary, we put points or not at the boundary, and it doesn't. It's changed your energy. It's changed your energy here finally. But it's for the same edge. Now it's important to say the same. The boundary condition comes from. If you mean, yes, maybe. Do you want I give more detail about that? Okay. I understand your problem. So boundary condition finally what we do now when you say in the different limit, you consider not really we fix a configuration, an outside configuration. Let omega bar a fixed outside configuration. And the finite volume Gibbs measure now is, let me just finish that. The finite volume Gibbs measure now is with this outside configuration is just this one. So you have an outside configuration, we fix it, and we put here this finite volume Gibbs measure for the energy in lambda with this outside configuration. And it is exactly what we did yesterday, but I write it a bit differently. But it's exactly what we did. So the problem here, now it's quite clear, these things converge. So this finite volume Gibbs measure with outside omega bar here converge to a Gibbs measure P omega bar. It depends on the outside configuration omega bar here. And the question is if this measure here depends on omega bar or not. And it's related to yesterday. And so if here we find two Gibbs measures, so we can find different omega bars such that the limit is different. It's just it's the first time up here. It's in a paper by Badley and Van Lieshout. And it was about Kerr mass process. But there is a more elegant proof using power tessellation. You can count.
What kind of tessellation?
Power tessellation is. It's just when you consider a configuration of ball, power tessellation is more or less a tessellation. It's a graph built on this point, on this ball. And these graphs try to find a minimal structure to describe the connection of the balls. For example, if there is another ball here, there is a graph is forgotten. So I cannot give precise definition here because I don't remind it. But the power tessel try to find a minimal structure to describe the connection of the ball. And with this minimal structure, it's quite easy to find the number of holes is just a loop here, and this number of loop is clearly bounded by a constant times the number of points. So it's the main idea of the power tessellation, and it was done in the paper of Müller.
But the number of loops, why bounded by number of vertices? You said that number of loops.
Yes.
Is bounded by, but it's bounded by number of edges, more or less.
Yes, but the number of edges
could be quadratic. And
the edge is quadratic. Yes, it's a problem. So you have to
modify the graph somehow.
Exactly. It's what you can do with power tessellation. I don't remind exactly how to do that, but it's what more or less you have to do. Exactly.
Looking just at the graph, you can't tell if it's a hole or not.
There's weights on edges. I mean, lengths of edges.
Yes, for respect to the.
So it's geometrical graph.
It's a geometrical graph. Yes.
Yeah, and loop doesn't mean that there is a hole. Yeah. For sure.
It depends. Yes, it's large. Okay. So I can give more detail.
It looks complicated, yeah.
Yes. And it's true in dimension 3. So, so try to build a structure with balls. Because it's more or less quadratic, I think. You can find quadratic configuration for the number of O's. It's not so much complicated, I think. Okay.
But it's on this graph, the idea of proof is in this graph model,
yes? Yes. Okay. I would like to give you the proof, so the existence of Gibbs measure. So it was the main idea of the lecture, to a proof of the existence of the Gibbs measure under the condition I gave. So the theorem I would like to show you is if H satisfies, so the assumption was stationarity, stability, hereditary, and finite range. It exists, then it exists Gibbs measure. If you want, yes.
No, it's not necessarily unique.
It's
not necessarily unique.
Yes, of course. No.
Like yesterday.
Like exactly yesterday, the error process is in this setting. The error process is exactly in this setting, and the Gibbs measure is not unique. But I recall it's only one example we have, more or less. There is another one with a very special potential, so the CAC potential, but with simple example, it's the only one we have, a phase transition result. But the existence is quite now well known, and with our method, it's a general method to build Gibbs measure and infinite volume model. And it's based, the main tool, so I will give it, but to keep in mind, what is the main tool is a specific compactness by specific entropy. So if you have just to keep in mind 4 words, what is the tool? Compactness by specific entropy. So I will try to explain you now. Okay. Maybe. Okay, what is the idea? It's just to build a probability measure by limit also, like yesterday, but in a different setting, different way. So we start first with a bounded window lambda n, for example, is equal to 0 n to the power d. And the finite Gibbs measure on this window. So like yesterday, Pn is just 1 over z lambda n without outside configuration. Or I can just put it like that. Okay? So here, let me just give a picture because I need after a more complicated thing. So this is 0, n, this is 1. And so I build on this block a finite volume Gibbs measure with outside configuration. If you have a look here, it's empty. But you can put what you want, but here it's an empty outside configuration because it depends only here. Finally, I just can write that. Empty configuration. So here it's Pn. You put Pn here. And now I need all this stuff here is in a stationary setting. So the compactness argument by specific entropy use a lot of the stationarity of your process. So, but this one is not stationary because it's only defined here. So I have to give a stationary version of this one. How to do it is just to consider copy of Pn in different block. So I consider different block here, and I put ID copies, independent copy of Pn here also, and so on. And this process here, the different copy of Pn, independent copy of Pn, I called it Pn at. Okay, so it's a copy. But it's not stationary for the moment, because if I consider a translation by vector 1, by vector 1, 1, it's not the same process because the boundary is different and so on. So I have to find a stationary version of this one, and for that I consider Pn bar is just I will put in lambda n randomly here a new origin. So it's just 1 over n to the power d, the sum for a new origin I in 0 n to the power d, and I consider this process Pn at translated at this new origin. So tau e is just the translation with vector by vector minus e. It's just an application on Rd to Rd, which x minus e. So this process is just, and divided by the number of new possible origins. So it's just this one, and I choose randomly a new origin on this block here, and I translate it. So now this process is a shift invariant with respect to the translation with integer coordinate. So in distribution, sorry, minus. So it's quite usual to do that. It's a special average of Pn. Special average of Pn. Okay. And now it's easier to try to prove this Pn bar converge to somebody that Pn. It's quite strange, but this one now, it's easier to prove that this one converges than this one. Because this one is stationary and you can use properties of the stationarity. And in particular, you use the specific entropy. So I need for that to define the entropy, which will be the tightness tool. So let P a stationary probability measure on omega. Any, not only this one, but consider any stationary probability measure on omega. First, we define the relative entropy. By what? Consider lambda included in RD. The relative entropy of P with respect to the Poisson process is just the classical entropy of P lambda respect to P lambda, the marginal, which is defined by classically the integral of F lambda log F lambda d P lambda if P lambda over P lambda is equal of F lambda. So if P lambda, the projection on lambda, the marginal law of lambda, of P on lambda, admits the density with respect to the Poisson process in lambda with the density F lambda, the entropy is just defined by the integral of the density, logarithm of the density over P lambda. In particular, it is defined because F lambda d P lambda, F lambda d P lambda is P lambda. So it's also equal to integral of F logarithm of F lambda dp lambda, dp lambda, and it's pi, sorry. Okay? And if otherwise, if the density does not exist, you just put plus infinity. Yeah. So it is the relative entropy of P with respect to pi on the set lambda. Now, what is a specific entropy? The specific entropy, which I called E of P, is just the limit when lambda goes to RD of this quantity here divided by the volume. Okay, it is a specific entropy. It's specific means when you divide it by the volume and you get the limit. Take the limit. Okay, it is a specific entropy. So, of course, it's not clear. This one is clearly defined. But this one depends if the limit exists. But finally, it always exists. And it's a result. And maybe I can give a proposition here about that. Finally, this quantity is increasing with lambda. So E lambda P is increasing with lambda.
It's increasing only under stationarity, or it's always increasing?
No, it's, this stuff it's only because we have stationarity here. So it's P is stationary. So and pi also. So this quantity, because we are in this setting, it's always increasing with lambda. Okay. So finally, this if this thing is increasing, it's just defined by the supremum. And this supremum is always defined, eventually equal to, maybe equal to plus infinity, but it's defined. And it belongs to R union plus infinity. So it's always, but it's always positive. So you can prove it by Jensen inequality. So it's in R plus union plus infinity.
But here we have only integer stationarity. sufficient?
Yes, it's true. Two ways you can consider only here a block in ZD here, or here you can consider a stationarity with an integral with respect to a new, but okay. I consider a block here lambda in ZD. It's okay?
Not really.
It's not important at all here. You can, in any case, you see I choose lambda n in the block in ZD. So, but you're right. Normally, so it's the first important property. The second one I would like to point out is it's an affine function. It means the entropy of alpha p plus 1 minus alpha q, if you consider two measures now, is just linear, it's affine, so it's alpha e of p plus 1 minus alpha e of q. So it's a nice, so it's only true at the limit. It's not true for the finite volume, the relative entropy. It's true by the specific entropy. This one is just convex or concave, I don't remember, but here you obtain that. Okay, so it's important property that I really use now. And all this stuff, I advise the book of Georgi, Phase Transition. There is a chapter about that in the book, and you can find all the proof of that. Okay, now what we can do. So P n bar is stationary, so we can compute. You can compute. You can try to compute the specific entropy, and the specific entropy of Pn bar here is finally equal to so we can, I don't know. Okay, I give the calculus here, it's not so important. We'll see after that. So let us compute the entropy of Pn bar. So Pn bar, it's, you see here, it's an affine decomposition of Pn chapeau, Pn hat here. So, and by stationarity, all these probability measures are the same specific entropy. So finally, the entropy of Pn bar is equal to the entropy of Pn hat, because it's an affine decomposition here, and by stationarity, all the probability measures are the same entropy. And so this one we can just write maybe the following. It's true by any increasing sequence of cube. So it's equal to the limit when k goes to infinity of the volume. Okay, I consider the relative entropy. So the relative entropy when on the cube minus key n and key n, yes, to the power d of Pn hat with respect to p, and I divide it by the volume of that, which is exactly 2kn to the power d. And it's a product here, so I can write the definition. The integral of the density on minus kn to the power d of Pn at with respect to P, and integrated with respect to Pn minus kn at d, and okay, just by definition. And this white we call, remember, P lambda hat here is just an independent copy, so the density is a product. And we consider the logarithm is missing. When we consider the logarithm, it's just a sum. And the sum here for k to the power 2k to the power d terms. And we find just the entropy, the relative entropy on lambda n of Pn. Yes, exactly. And it's just equal to the limit when it's not a limit, so finally it's not a limit because the k is disappeared here, and we just find finally here the entropy of Pn on lambda n with respect to Pn. P lambda n. Okay? And okay, so it's quite simple here. And we can compute this quantity here. So E lambda n, Pn P lambda n. So it's just the integral, the logarithm of the density. The density is not written, but never mind. Pn, and so minus logarithm Zn minus the integral of h dPn. And now we use here so this first term, it's quite easy because Zn is bigger so Zn simple minus here, there is minus here, so Zn is bigger to, we give the calculus before, exponential minus z lambda n. So this quantity here is smaller than z lambda n. And this quantity by stability is smaller by the constant of stability, I call it C. So integral of number of points. dPn. Okay. And so it's this fact here is just the mean number of points in lambda n under Pn. Okay, so just the proposition I would like to give now is the following one. So the entropy, the entropy of Pn bar, specific entropy of Pn bar is smaller than Z. We divide it by the volume here. Yes, something is missing, n to the power d. We divide it by the volume of lambda n, so it's smaller than Z. plus, and this quantity is C times this. When we divided that by the volume of lambda n is just equal to the intensity of the process P n bar. It's a mean number of points of P n bar. Okay, this just defined by, for example, the expectation of bistationarity of the cardinality of omega under P n bar of omega on the 0.01 superods. The mean number of points of P n bar. Okay? And okay, so it was quite simple to obtain this domination, which is so the constant z, of course, and c are uniform in n. And now the main tool from specific entropy, that it claims that this kind of uniform domination is enough to have compactness for the L topology, the local topology. So for that, I would like to be precise. This fact was not really related to Gibbs measure. It's not really new, but what we have is following proposition by Dereudre. You can find also in this book and the same chapter the specific entropy. If you consider let's say let A be a constant. So, and the following set is a set of probability measure P. The set of probability measure P such that the specific entropy is bounded by A. Family of all probability measure on omega such that the specific entropy is uniformly bounded is sequentially compact for the local topology. So the local topology claims is just, this one is just so it just mu n converge to mu for this topology if for any bounded local function of course. Okay, so it's a very strong result. It's not so easy, of course, to prove it, but you can find the proof in the book of Dereudre. And so I would just to claim it's not the weak topology here. The function is not assumed to be continuous or something like just. The function is just assumed to be local. And of course measurable. It's not written, but it's necessarily measurable. So it's just for bounded, measurable, and local function. You have the convergence of that to that. So it's very strong and very difficult to have this kind of thing. But it's done for any sequence, for example, for a subsequence of probability measure with a bounded specific entropy. So it is here the main tool we use for proving the convergence of the finite volume Gibbs measure here. Okay. So at this stage there is a small problem because here we have this part here, and maybe this part is going to infinity if there is an explosion. Okay, if the mean number of points admits an explosion, so this thing goes to infinity, and so we are not in the level compact set of the specific entropy. So we can solve this problem by a change of intensity. I will explain you quickly. Let us consider now two intensities, Z and Z prime. So yes, Z prime, two intensity. Here, in this computation, I compute the specific entropy with respect to Z. I fix Z, the intensity, and I compute the specific entropy with respect to Z, because pi was everywhere pi of Z. Okay? So now, if I compute the specific entropy of a measure, but for another intensity. So I compute, for example, this quantity here. So I put now the intensity parameter here. I compute the entropy of P with respect to pi lambda Z prime. So what is exactly? So we can put a lambda here. It's the density of the logarithm of the density f lambda with respect to so the density, I write like that, p lambda with respect to p lambda Z prime dp lambda. Okay. Now I can change the density. Can write the density of p lambda with respect to pi lambda Z, pi lambda Z, and pi lambda Z prime. Of course, the log of product becomes a sum. So I recover the density here. Plus the logarithm of the density of this Poisson process with respect to this one, integrated with respect to P lambda. Okay, so this part I recover the old entropy. Here, this one is just the entropy with respect to now to Z. It's the old one, and this one. So we can compute easily the density of two Poisson processes with respect to each other, and maybe I can write here's the density. It's not complicated to see that the density P lambda Z with respect to P lambda Z prime is just Z over Z prime times the number of points. And of course the normalization constant gives a constant exponential Z prime minus Z times lambda. Okay, so you can compute the density here and put that here, and we obtain finally logarithm of Z over Z prime integrable of cardinal of point dp plus Z prime minus Z times the volume of lambda when you compute here the difference of entropy. Okay? Okay. And so when you divide it now by the volume and we get the limit, here we obtain the specific entropy of P with respect to Z prime is equal to the specific, so this part gives the specific entropy of P with respect to Z, plus here this quantity here the logarithm of Z over Z prime, and this quantity is just equal to the divided by the volume the intensity of P. Yes, it's good. Nothing. And this quantity is just divided by the volume Z prime minus Z. Okay. So now look at here. If I choose this quantity, now I can choose Z prime like I want. Because Z is fixed, it's the intensity of our parameter, but I can choose Z prime like I want. So choose Z prime such that this quantity log Z over Z prime is exactly equal to minus C. So I can do it, of course. And so we find here, so using this quantity here, finally it's a kind of intensity with respect to Z. Okay, so I find that the specific entropy with respect to Z prime of P n bar is just equal to this quantity, so Z, plus C ZP, so I just recall P n bar, and this quantity is minus C Z of P, it's clear, plus Z prime minus Z. It's smaller than that. And so finally we find it's smaller than Z prime, and the other part disappeared. So it's bounded. So it's quite miracle when you change. So when you change the intensity parameter of the reference measure for computing the specific entropy, this annoying term, constant time Z over the intensity of this process, disappeared. And so finally we find that the sequence of specific entropy for Pn bar we built with respect to the Poisson process with the intensity Z prime is uniformly bounded. And by the compactness argument here, it's tight for the local topology. So we can extract a convergent subsequence. So we can extract a subsequent convergence. To a limit point which we call P bar. Yeah. And P bar, so P bar is a Gibbs measure. P bar is a Gibbs measure, the existence Gibbs measure. So this construction can be done for the model of yesterday, for the model of a rare process, or for any model I give the assumption before. And you obtain a limit point. So it's it remains to normally to. Do you want I finish definitely the proof, or we can finish here? So last part it's not so important, but it's not finished. We have a limit point, but are we sure that this limit point satisfies the DLR properties, the definition of Gibbs measure? So maybe I can skip this part. It's not difficult, and at this part, because for the moment we don't use the finite range, the finite range assumption here. But for the last part, we will use it because more or less what is the idea? Pn is a finite volume Gibbs measure. So finite volume Gibbs measure by the Markov property, it satisfies the DLR equation. It's exactly the Markov property I gave at the beginning of the course. And so like Pn converges to P bar, more or less Pn is just a modification of Pn. And since the interaction has a finite range, the kernel probability is finite range, and it's a local function, because this convergence is just for local function. And the Gibbs kernel is local in this case, and so we can recover at the limit the DLR equation for Pn bar, for P bar. Yeah. So the details I can give you maybe off or another day the details of this, but it's quite simple. It's quite simple. You can keep in mind this idea. When the interaction has a finite range, it's quite simple to obtain the DLR equation for the limit point if you can prove the limit point exists. Okay, so but it's a classical argument. It's not really new. What is really new? It's very recent. This strategy appears in our paper with Georgi and Dereudre, and we give a lot of examples of Gibbs measure, more complicated than that, but included this one. And what is really new is to use the specific entropy tool for as a compactness tool. So it was what I would like to present you today, and I use also this argument for build stochastic differential equation, infinite Gibbs measure with in non-compact set. So this tool is really powerful in a large class of model, and okay, so maybe you can use it for your stuff also. Okay, so it's the end of this second lecture. Thank you for your attention.